Hi, I'm Miss Hearn. Let's get started. This is part 3 of a video series on reviewing for our intermediate algebra final. We're going to look at rules of radicals and exponents, items number 26, 40, 9, 10, 38, 11, and 35 on your final exam review. We're going to start with the rules of exponents. We have that when we multiply like bases, b to the n times b to the m, we add their exponents, b to the n plus m. When we divide like bases, we subtract the exponents. When we raise a base to the 0 power, we get 1. When we raise a base to a negative power, that's the same as taking 1 over the base to the positive version of that power. When we raise a product to a power, we can just raise each part to that power, but that doesn't work for a sum or difference. For example, a plus b to the n is definitely not equal to a to the n plus b to the n. That's a very common error that you should try to avoid. It is true, however, that if we divide a by b and raise that whole quotient or fraction to the power, we can just raise each part to that power, a to the n over b to the n. And also, we know that if we raise a power to a power, we multiply the exponents. So the quantity a to the n, then raised to the m power, is a to the n times m. Now, it turns out that exponents and radicals are actually just a different way of writing the same concept. So, for example, the nth root of a to the n is a to the n over n, and the mth root of a to the n is a to the n over m. The index is the denominator of the exponent, and the power is the numerator of the exponent. Now, in the case of nth root of a to the nth power, a to the n over n is a to the 1, which is just a. And that's going to be important as we work through simplifying some of these expressions. So here we go. Let's start with item number 26. In this item, in the numerator, we have y to the 1/3 times y to the 2/5. When you have like bases, the y's, we can, and they're being multiplied, we can just add the exponents. So in the numerator, this is going to be equivalent to y to the 1/3 plus 2/5. Now you can either use your TI-30X2S calculator, or you can get a common denominator manually and add these together. So the common denominator of 3 and 5 is 15. So we're going to think of this as something over 15 plus something over 15. To get 1/3 to have a denominator of 15, we have to multiply the numerator and denominator by 5. 1 times 5 is 5, so 5/15 is the same as 1/3. To get 2/5 to have a denominator of 15, we have to multiply by 3 over 3. 2 times 3 is 6. So we have y to the 11/15 divided by y to the first. By the way, the power of 1 is not written, but it's assumed to be there. And so now we're going to have a quotient of like bases. When you divide like bases, you subtract the exponents. So you would have y to the 11/15 minus 1, but 1 could be thought of as 15/15, couldn't it? So subtracting 11/15 minus 15/15, we get y to the -4/15. We don't like to usually leave negative exponents in our answers though, so remember, the negative is just telling you it's on the wrong side of the fraction bar. We need to flip it over. So we have 1 over y to the 4/15. Now let's look at item number 40. Here we have inside the parentheses a product, and then that product is being raised to a power. Since we have like bases inside the parentheses, we can go ahead and add the exponents. So inside of the parentheses, we have x to the 4 plus 3. You don't have to write that step, but just so you see, that's what we're thinking. So this is really going to be x to the 7th power raised to the 3/2 power. Now when you raise a power to a power, you multiply the exponents. So this is going to be x to the 7 times 3/2. Once again, you could use the fraction operation on your calculator, or you can just go ahead and multiply this out yourself. Thinking of the whole number as being over 1, you can just multiply straight across. So this gives us x to the 21/2 power. Now let's look at item number 9. Item number 9 asks, what's equivalent to 27 to the negative 2/3 power? Now, our final exam is multiple choice, and in some cases, the way the answer is written is not necessarily determined by the instructions. Like in this case, there are several ways we could write an expression equivalent to 27 to the negative 2/3. So let's look at some possible multiple choice answers. So in item number 9 on our final exam review, it appears as though they want us to start with an expression that has a rational exponent, a fraction in the exponent, and rewrite it in radical form. So in order to do that, we need to do two things. First, you always deal with a negative in an exponent before you try and switch to a radical notation. So we're going to think of this as 1 over 27 to the positive 2/3 power, right? A negative exponent just means it's on the wrong side of the fraction bar. And then we're going to use our knowledge of fractions in the exponent. We know that a base b raised to the n over m power is the same as the mth root of b to the n, where the denominator of the power is actually the index of the radical. So in our case, what we have is 1 over, and then we have the cubed root of 27 squared. So that would be answer B. Now let's look at item number 10. So for number 10, we need to add two radicals. The way that we add radicals is they must be identical, and we add their coefficients. In other words, we have to have like radicals. These two radicals are not in a simplified form because there's a factor of each of these numbers, 8 and 18, that's a perfect square, which means the radicals could be simplified. In order to determine if we are in simplest form, we're going to find the prime factorization of each of these numbers. Primes are numbers that can't be divided by any number other than itself in 1, like the number 2, the number 3, 5, 7. 9 is not a prime because 3 goes into it evenly, but 11 is a prime, 13, and so on. To get the prime factorization of the number 8 means to write it as a product of primes. To find a prime factorization, I like to use the ladder method. So what we do is we divide 2 into 8, and it goes in 4 times. 4 is not a prime, so we keep going. If we can divide by 2 again, we do. If not, we move to the next prime. 4 is divisible by 2, and it goes in twice. We stop here because we've reached a prime. That means it can't be divided by any other factors. So 8 is actually going to be equal to 2 times 2 times 2, or 2 to the 3rd power. So I'm going to think of this not as the square root of 8, but the square root of 2 to the 3rd. Let's do the same thing with 18. So 18 divided by 2 is 9. 2 can't go into 9, so we go to the next prime, which is a 3. 3 goes into 9 3 times, and we stop because we got to another prime. So the prime factorization of 18 is going to be 1 copy of 2 times, notice that we just found this copy of 2, but we also have 2 factors of 3. So it's going to be 2 times 3 squared. So I'm going to write this square root of 18 as square root of 2 times 3 squared. Now the next thing I always do in order to simplify each of these radicals is break it apart into 2 separate radicals. One with the perfect squares and one with the leftovers. For example, 2 cubed is not a perfect square, but we can break it apart into 2 squared multiplied by 2. Plus 18 was 2 times 3 squared. If I break this apart into perfect squares and leftovers, 3 squared is a perfect square and 2 isn't. The reason why I do this is because the square root of a perfect square, remember you're dividing 2 by the index 2. 2 to the 2 over 2 is just 2, and the radical goes away. But there's nothing you can do with the leftovers. They stay under the radical. Plus the square root of 3 squared, well again, the power 2 divided by the index 2 leaves 3 to the 1st power, just 3. And then we have the square root of 2. Now we have like radicals, so all we have to do is just like adding 2x plus 3x. We can add the coefficients and get 5x. But in this case, we're not adding 2x and 3x, we're adding 2 root 2 and 3 root 2, and we're going to get 5 square roots of 2. And that's the final answer for this one. Now let's look at item number 38. It says simplify 3 root 54 plus 2 root 24. Once again, we're being asked to add expressions that have radicals. And the only way you can do that is if you have like radicals. That means they're identical. Same index, same radicand, and we don't have that situation here. But it's possible these radicals can be simplified. So I'm going to go down here and just focus on simplifying, and then we'll come back to this expression in a minute. The square root of 54, for example. How can we simplify that? So I'm going to look for the prime factorization of 54. So what do? We think of our prime factors, 2, 3, 5, 7, 11, 13, and so on. And you start with the smallest and you see, does that go into 54? 2 does go into 54. 54 is an even number. 2 goes into 54 27 times. But 2 can't go into 27, so we're going to move to the next prime, 3. Can 3 go into 27? Yep, it goes in 9 times. 9's not prime, so we check, does 3 go into 9? Yes, it does. It goes into 9 3 times. And then we stop because we got to a prime. So now we're going to say that 54 could actually be written as 2 times 3 times 3 times 3. Or in other words, 2 times 3 to the third power. So when we're simplifying the square root of 54, we have to think of it as the square root of 2 times 3 cubed, which we will break apart into a square root containing perfect squares and a square root containing the leftovers. 2 doesn't have a power at all, so it goes into the leftovers. 3 cubed has a power higher than the index of 2. 3 isn't divisible by 2, but we could break this apart into 3 squared times 3. Remember, when you multiply like bases, you add the exponent. So 3 squared times 3 to the first is 3 cubed. 3 squared is a perfect square, and then the part we broke off, the 3, goes into the leftovers. So the square root of 3 squared is 3 times the square root of 6. So in our original problem, the 3 root 54 would be 3 times 3 root 6. Now let's figure out the square root of 24. So square root of 24, we're going to say 2 goes into 24 how many times? 12. Does 2 go into 12? Yes, so we'll divide it again. 2 goes into 12 6 times. Does 2 go into 6? Yes, so we'll divide it again. 2 goes into 6 3 times. So 24 is a product of 2 times 2 times 2 times 3. Or in other words, 2 to the third power times 3. So when we find the square root of 24, that's the same as finding the square root of 2 cubed times 3. Which will break up into our perfect squares and our leftovers. So 2 to the third is not a perfect square because it has an odd exponent, but we can break it apart into 2 squared times 2. Break off a factor of 2 and we're left with 2 squared, which is a perfect square, and 2, which goes in the leftovers. 3 is also going to go in the leftovers. Square root of 2 squared, the exponent divided by the index is 1, so we just get a 2. Times the square root of 2 times 3, which is root 6. So in our original problem, 2 root 24 would be the same as 2 times 2 root 6. 3 times 3 root 6 is 9 root 6. 2 times 2 root 6 is 4 root 6. Notice that now we do have like radicals. And if you have like radicals, you can just add the coefficients, the numbers in the front. So 9 plus 4 is 13 square roots of 6. Now let's look at item number 11. We're supposed to find the product square root of 6 minus 2 times square root of 6 plus 2. Now the first thing that you should notice is that we can't work inside the parentheses because square root of 6 minus 2, these are not like terms or like radicals. 2 doesn't have a square root of 6 attached to it, so there's nothing we can do with that. Also, square root of 6 cannot be simplified. The prime factorization of 6 is square root of 2 times square root of 3, which has no perfect squares. So that can't be simplified any further. Same thing with square root of 6 plus 2. So the only way we could perform this operation would be to treat this like we normally do binomials. That just means two terms, right? So when you multiply two terms times two terms, you can FOIL it out, or in this case, these happen to be conjugates. Conjugates are the same two terms, but with the opposite sign in the middle. We've seen many times the use of conjugates in factoring and multiplying polynomials. For example, a minus b times a plus b. When you FOIL it out, the middle terms cancel and you're left just with a squared minus b squared, a difference of squares. So we can also, instead of FOILing it out, we can use this pattern. When anytime you multiply conjugates, you get a difference of squares. The first term squared minus the second term squared. In this case, that would be square root of 6 squared minus 2 squared. Square root of 6 squared, the square root reverses the squared and we're left with just the 6, minus 2 squared, which is 4. 6 minus 4 is 2, and we're done. Now let's look at item number 35. This is different than the other radicals we've been looking at because it has what's called a higher order index. That means an index that's higher than 2, in this case 3. So when you're working with simplifying a radical with a higher order index, you look at the value of the index, and what you're going to want to do is to find, in this case, perfect powers of 3, or any power that's divisible by 3. Because remember, the nth root of x to the m is going to be x to the m over n, the power divided by the index. So we can simplify any radicals where the m is a multiple of n. So let's go ahead then and try and break this apart into a radical that has all the perfect cubes, perfect powers of 3. Those are things where the power is a multiple of 3. And then we're going to have the leftovers. Okay, but before we can do that, we have to deal with this number 250 and finding its prime factorization. So the way you find the prime factorization of 250, think about the prime numbers 2, 3, 5, 7, 11, 13, so on. Start with the smallest prime and divide into 250 if you can. 2 goes into 250 evenly, 125. But can 2 go into 125? No. 125 is not an even number. So then we move on to 3. Can 3 go into 125? Well, 3 goes into 12 4 times, but 3 goes into 5 with a remainder. So no, 3 does not go evenly into 125. So now we're going to move on to 5. 5 goes into 125 25 times. Can 5 go into 25? Yes, it goes in 5 times. And now we're going to stop because we got to a number that's prime. It's on our list of primes. So now we're going to say, okay, that means that 250 could be written as the product of 2 times 5 times 5 times 5. Or in other words, 2 times 5 cubed. All right, so now let's go ahead and break up our radical into the perfect cubes and the leftovers. So 2 is definitely in the leftover category because it has no power. 5 cubed goes into the perfect cubes category. X to the 7th is tricky. The 7, the power 7, is bigger than 3, so we're definitely going to be able to break it apart and put something into the perfect cubes. What you want is the highest multiple of 3 less than 7. So what are multiples of 3? 3, 6, 9, 12. These are all multiples of 3. The biggest one less than 7 is 6. So we're going to break apart x to the 7th and think of it as x to the 6th, which is a perfect cube because it's got a power that's a multiple of 3, and then times x to the 1st. So that one is in the leftovers. How about y to the 14th? What's the biggest power of 3 less than 14? Well, that would be 12. So we're going to break this apart into y to the 12th times y squared, which goes in the leftover. Now we're going to simplify everything that's in the radical that's got all the perfect cubes. So the cubed root of 5 cubed is just 5. The cubed root of x to the 6th, you divide 6 by 3 and you get x squared. The cubed root of y to the 12th, divide 12 by 3 and you get y to the 4th. And that's going to be multiplied by all the leftovers, 2xy squared. And that's as simple as that cube root can be. I hope you found this video helpful. If you did, please remember to give it a thumbs up. That helps other students to find the video.